Let's learn about derivatives of trigonometric functions. In this first problem, we start with using the angle sum identity that you see here. Sine of alpha plus beta equals sine of alpha times cosine of beta plus cosine of alpha times sine of beta, as well as calculator estimates of a couple of limits to verify that the derivative of sine of x equals cosine of x. Before we start this, you should understand that it will be important for your calculator to be in radian mode. Otherwise, you'll get the wrong answer. It's not explicitly told us here, but evidently we must need to use the limit definition of the derivative that's implied by the fact that we're talking about estimating some limits here. So the derivative with respect to x of sine of x, also written sine of x prime, by definition of the derivative, is the limit as h goes to 0 of sine of x plus h minus sine of x, all divided by h. To this point, you may be used to doing limit calculations like this with polynomials, for example, and you ultimately end up canceling terms in the numerator that don't involve h and factoring h out of the numerator and canceling it with the h on the bottom before you plug in h equals 0. How in the world can you possibly do that here? You really can't. Sine of x plus h does not equal sine of x plus sine of h. Hey, but there is this angle sum identity. We must have to use that here. Yeah, replace alpha with x, replace beta with h. Let's go ahead and just see what happens. It does look like it's going to be more complicated. We're going to get sine of x times cosine of h, and then plus, again using this angle sum identity, cosine of x times sine of h. And then don't forget the minus sine of x right there. It looks worse, but it is actually better. Just keep going. Try various things and see what happens. One thing that's often useful in these kinds of situations is to identify any common factors in more than one term. For example, both this term and this term have a factor of sine of x. If you group those two terms together, you could factor that sine of x out. Is that a useful thing to do? Possibly, because when you do this calculation, you're letting h go to 0. You're treating x as a constant. Maybe we can factor that out of the limit sign. Yeah, that's supposed to be the bright idea to help you finish this. You can also break this into two limits, because you can break the fraction into two fractions. I'll group these two terms together in one fraction, and I'll put this term in another fraction by the definition of how to add fractions. I'm going to break the fractions apart here. The limit as h goes to 0 of the first two terms with the sine of x factored out, the two terms that I've circled there, sine of x, and in parentheses cosine of h minus 1 divided by h. I'm also going to right away use the fact that the limit of a sum of two things is the sum of their limits. So I'm going to write plus the limit as h goes to 0 of this thing right here, cosine of x times sine of h over h. All right, yeah, now with this expression right here, the sine of x, with respect to the limit at least, is a constant. When you do this calculation, you want to think of x as fixed. Factor it out. Hey, and that can happen in the second limit here too. This cosine of x is a constant. That can be factored out as well. So what we're left with is sine of x times the limit as h goes to 0 of cosine of h minus 1 over h plus cosine of x times the limit as h goes to 0 of sine of h over h. Now, if nothing else, these limits expressions that you see here are simpler than they were before in a sense. These limits don't involve x for one thing. They are simpler. Yeah, maybe we can use technology. That's the point now, is to use technology, and this is where your calculator has to be in radian mode to finish this correctly. So for example, we could graph these functions of h. Okay, of course in a calculator it's going to look like an x. You got to use an x, but it's the same idea. Let me go ahead and type cosine of x, representing cosine of h, minus 1, all divided by h. which you have to type in the calculator as x. And I'll also graph this other function, sine of x, or sine of h, divided by h. I'll graph them both and see what happens. Again, make sure your calculator is in radian mode. Well, I'll double check that here. The mode is, yes, radian mode. Oops. Radian mode, not degree mode. If you use degree mode, you get the wrong answer. The assumption in all of this with these trig functions is that your input is in radians. Pick a window. I went negative 2 pi to 2 pi. I'll just keep it like that. Let's just see what happens. So the first graph is going to be the graph of cosine of h minus 1 all over h. There it is. Zoom. It looks like it's approaching 0 as h approaches 0. And here's the second graph, sine of h over h. It looks like it's approaching 1. The highest value here is 1. Is that correct? I'll leave it to you to check that if you plug in values of h close to 0, but not equal to 0 because you'd be dividing by 0, the first limit seems to be 0 and the second limit seems to be 1. And in fact, that is true. This limit right here does turn out to be 0. This limit right here does turn out to be 1. Technically speaking, you know, the calculator is hiding the fact that the graphs would have holes in them. You don't see the holes there. Obviously, the calculator is just connecting dots. No vertical asymptotes. These limits exist. This one's 0, this one's 1. And so this thing becomes 0. This becomes cosine of x times 1. And therefore, the answer is cosine of x. We're done. The derivative of sine of x is cosine of x. We have confirmed this, assuming x is in radians. Part B says to use the Pythagorean identity. This is kind of fun here in Part B. Use the Pythagorean identity and the fact from Part A to confirm that the derivative of cosine of x is not sine of x, but negative sine of x, the opposite of the value of the sine function. Well, what's the Pythagorean identity, first of all? It's the fact that cos squared x plus sine squared x equals 1 for all x. This is not an equation to solve. You would never look at this equation and say, I have to solve for x. It's an identity, which means it's true no matter what x is. For all x, if you graph cos squared x plus sine squared x, meaning cosine of x quantity squared plus sine of x quantity squared, on your calculator, it will be a horizontal line, amazingly. That's an amazing fact right here. How in the world can we use this, as well as the fact that the derivative of sine of x is cosine of x, to derive the derivative of cosine of x to be negative sine of x? Well, maybe you've done problems like this before, maybe you haven't. What you want to do is just differentiate both sides and pretend like you don't know what the answer is for the derivative of cosine. Go ahead and do that. You do need the chain rule here. This is kind of a preview of implicit differentiation, actually. When you differentiate cosine of x quantity squared, the inside function is cosine of x, and the outside function is the squaring function. The derivative of this is going to be, you have to take the derivative of the outside function. The derivative of x squared is 2x. But then you got to plug in the inside function into that, so I replace x with cosine of x. Then the chain rule says to also multiply times the derivative of the inside function, the derivative of cosine of x, which we're pretending we don't know. So we'll just write it as d dx of cosine of x. That's the chain rule. We do know the answer, but we've got to pretend we don't know. We're trying to derive the answer. Do the same kind of thing with this function right there, the derivative of sine squared x. Bring down the 2. I'm using the chain rule. Get 2 sine of x times the derivative of sine of x. Now, I could go ahead and write d dx of sine of x, but I already know the answer is cosine of x. Let's go ahead and use that. And then, if you differentiate the left side, you got to differentiate the right side to still get an equality. The derivative of 1 is 0. Hey, this is an algebra equation that we should be able to solve for the derivative of cosine of x. Yeah. Subtract this from both sides. I'll go ahead and do 2 steps here. 2 cos x times d dx of cos x will be negative 2 sine x cos x. And then divide both sides by cos x and also 2. And you'd say the derivative of cosine of x is negative 2 sine x cos x, all divided by 2 cos x. And then, yeah, cancel the 2's and cancel the cosine of x's. Divide them out. Is this valid, you might wonder? It's valid as long as you're not dividing by 0. Now, certainly the cosine function is 0 at certain spots, like pi over 2 and 3 pi over 2, etc. So this is no proof. It's a confirmation, you might say. That's what I asked you to do here, is confirm a derivation. It's not a proof that the derivative of cosine of x equals negative sine of x, except when cosine of x is non-zero. Then you might wonder, well, what about when cosine of x is 0? Well, okay, it's not a full proof then. But I think it's kind of fun, a fine derivation of the fact that the derivative of cosine of x is negative sine of x. On to part C. Find the second derivative with respect to x of sine of x and the second derivative with respect to x of cosine of x. Well, the second derivative of a function is the derivative of the first derivative. So the second derivative of sine of x is the derivative of sine of x. You can just use prime notation if you prefer here, but I kind of like ddx notation. It's fun. We already found the derivative of sine of x is cosine of x. And we also just derived that the derivative of cosine of x is negative sine of x. Interesting. The second derivative of the sine function is the opposite of itself. Weird, but true. What happens with the cosine function? What's its second derivative? It would be the derivative of the derivative. We just derived that the derivative of the cosine function is the opposite of the sine function, negative sine x. And the negative sign can come out in front, so I get negative times the derivative of sine of x, but the derivative of sine of x is cosine of x. Hey, the second derivative of the cosine function is the opposite of itself as well. Wow, kind of wild. Part D says, make sense of all this graphically. I won't write anything down, but let's use the calculator. Let's graph the sine and cosine functions. Go back here and delete these. Sine function, make sure you're in radian mode again. Cosine function, again my interval, x is going between negative 2 pi and positive 2 pi, y is going between negative 1 and 1. First function is the sine function, here it is. Second function is the cosine function. Okay, how to make sense of this graphically? Let me just verbally describe this. The derivative of the sine function is the cosine function. So the cosine graph, which is this one, tells you about slopes of the sine graph. The derivative of, the cosine graph is this one. Sorry, I made a mistake. This function tells you about slopes of this function. The slope of this function, the sine graph, is positive right there, just like and over here as well, just like the cosine graph is positive. The slope of the sine graph is negative, for example, right there, just like the value of the cosine function is negative. And you can continue thinking about that. Also, the derivative of the cosine function is the opposite of the sine function. So the opposite of the values of the sine function tell you slopes of the cosine. Here's the cosine. Its slope here is negative. The value of the sine function is positive, but the value of the negative sine function would be negative. Over here, the slope of the cosine function becomes positive. The value of the sine function is negative, but its opposite would be positive. And since the second derivatives of these functions are the opposites of themselves, the signs of their opposites tell you about concavity. For example, focus on the cosine function here first, or the sine function, let's do. It's concave down here. Its second derivative is negative. The value of the sine function here is positive. The value of its opposite is negative. Likewise over here, it's concave up. Its value is negative, but its value of the opposite is positive. The second derivative is positive here. Same kind of thing happens with the cosine function. Okay, so that's not a proof by any means, but it does make sense of things graphically. Part E says, find the 31st derivative of the sine function. What? You gotta be kidding me. Oh, it's not as hard as you might think. So the first derivative of the sine is the cosine. The second derivative of the sine function is the negative of the sine function. Think about it. The third derivative would have to be the derivative of this, which would be the negative of the cosine function. The fourth derivative would have to be the derivative of the negative of the cosine function, which is back to positive sine. Every fourth derivative brings you back to the sine function. The fourth derivative of sine of x is sine of x. And also the fourth derivative of the cosine of x is cosine of x. So the eighth derivative of sine would be sine, and the 12th, and the 16th, and the 20th, and the 24th, and the 28th, and, okay, 32nd would be back to sine, so 31st must be negative cosine. The 31st derivative, don't want to use 31 primes there, of the sine function is negative cosine of x, because the 32nd derivative would be, the derivative of this would be back to the sine function. In number 2, we continue with more derivatives of trigonometric functions and related functions. Part A says, find the derivatives of the tangent function and the cotangent function. I'm using a different variable for some variety here, theta. All right, so the derivative of the tangent function. F of theta is the tangent function. You first need to know the definition of the tangent function. It's sine of theta divided by cosine of theta. Sine theta divided by cos theta. I won't bother with parentheses like I have up here to save some time. If we're going to differentiate that using what we did in number 1, we're going to also need the quotient rule. Low d high minus high d low over the square of what's below. That's the way I say it. Low is cos theta. D high is the derivative of sine theta, which is cos theta, minus high sine theta. That's the high function. D low means times the derivative of the cosine function, which will be negative sine theta. If you're writing it there, use parentheses around that to emphasize you're multiplying there. You can also put a dot in there like I did. Divided by the square of what's below, divided by cos squared theta. So you get cos squared theta plus sine squared theta over cos squared theta. But cos squared theta plus sine squared theta, that's 1. Remember that identity from the previous problem? The answer is 1 over cos squared theta, which is also the same as secant squared theta. So the derivative of the tangent function is secant squared theta. Is that useful, you might wonder? You might wonder, who cares about the derivative of the tangent function? It actually comes up in more applications than you might expect, mostly actually with finding what are called antiderivatives, or antiderivatives if your teacher says it that way, of things involving the secant, which do come up in some applications. All right. What about the cotangent function? If g of theta is cotangent theta, well, what is that? That's, by definition, the reciprocal of the tangent, which is cosine theta over sine theta. So that means g prime of theta, once again, we need the quotient rule. Low d high, derivative of cosine, is negative sine theta, minus high cos theta. D low, the derivative of sine theta, is cos theta. Over the square of what's below, the top's going to simplify to negative 1, right? You'll get negative sine squared theta minus cos squared theta. The negative sign can be factored out as a negative 1, essentially. And you'd have sine squared theta plus cos squared theta, which is 1, the Pythagorean identity. So we get negative 1 over sine squared theta. That is the answer. You can put the negative sign in front. You can also write 1 over sine squared theta as cosecant squared theta. Okay, the derivative of cotangent theta is negative cosecant squared theta. For fun, you might want to graph these things on your calculator, and extra confirmation as well to confirm that these are the right answers. Derivative of secant is the next one. Going back to x. F of x is secant of theta, secant of x. That, by definition, is 1 over cosine of x. So the derivative of this, I once again need the quotient rule. Low d high is going to be 0, right? Because the derivative of 1 is 0. Minus high d low is going to give us this over the square of what's below. So we get sine x over cos squared x. It's common to write that as sine x over cos x times 1 over cos x. That's tangent, that's secant. Tangent of x times secant of x, or if you prefer, secant of x times tangent of x is the more common way to write it. That's the derivative of secant. It's related to secant. It's got a secant in it. Cool. How about the cosecant? G of x is the cosecant function. 1 over the sine function. Maybe you want to do this one on your own before you watch me do it. We need the quotient rule. Low d high is once again 0. Minus high d low is going to be minus cos x over the square of what's below. That's going to ultimately be negative 1 over sine x times cos x over sine x. More commonly, that's written as negative cosecant x cotangent x. I'm using the definitions of the trig functions here, okay? I'm assuming you're familiar with those things. All right, part C. Find and simplify the derivative of f of t equals e to the negative 2t cos 3t plus e to the negative 2t sine 3t. Yikes. Kind of complicated. Need the product rule and the chain rule as well as what we just found with derivatives of cosine and sine. So it's a pretty important kind of function. Comes up in a lot of applications with, for example, oscillating mass in a spring, where the oscillations get smaller and smaller over time because of friction, essentially. So take it step by step. What's the derivative of this? I need the product rule. So here I'm differentiating e to the negative 2t times cos 3t. The first function is e to the negative 2t. The second function is cos 3t. The derivative of e to the negative 2t, the first function, by the chain rule is negative 2 e to the negative 2t. Then that gets multiplied times the second function, cos 3t, plus the first function times the derivative of the second. E to the negative 2t is the first function. The derivative of cos 3t, I need the chain rule. The derivative of cosine is negative sine. 3t would get plugged in, then I'd have to multiply times the derivative of 3t, which is 3. So I get careful about signs here. I need that negative sign in there. Negative, ultimately 3 sine 3t. That's the derivative by the product rule so far of this first term. What about the second term? It's going to be similar. Once again, e to the negative 2t is the first function. There's its derivative. Times the second function plus the first function times the derivative of the second. The derivative of sine 3t by the chain rule will be 3 cos 3t. Simplify, you can combine like terms. This can combine with this, and this can combine with that, and we do get a bit of simplification. Negative 2 plus 3 is 1. We're going to get just 1 times e to the negative 2t cos 3t. And with the sine one, we have a negative 3 and a negative 2. That's going to give us minus 5 e to the negative 2t sine 3t, if I've not made a mistake. Here I'm actually going to check to see if it's right or not. There we go. It is right. I'm using this program called Mathematica to double check that it's right. All right, let's go on to the next part. Find the derivatives of f of x equals e to the sine of x and g of x equals sine of e to the x. I'm composing two functions. I need the chain rule. It's the same function, sine of x and e to the x, but opposite orders of composition. For this one, the inner function is sine of x, and the outer function is e to the x. For this one, the inner function is e to the x, and the outer function is sine of x. So if f of x is e to the sine of x, practice with the chain rule here. Inside function is sine of x, outside function is e to the x. The derivative of the outside function is e to the x. But then plug in the inside function. Don't forget to multiply times the derivative of the inside function. There's the derivative of e to the sine of x. G of x is sine of e to the x. The inside function is e to the x. The outside function is sine of x. The derivative of the outside, sine, is cosine. But plug in the inside, then multiply times the derivative of the inside. Okay, so those are pretty quick. Part E is actually pretty quick as well. We, in fact, have already kind of done it. Find and simplify the derivative of h of x equals cos squared x plus sine squared of x. We've done this before. H prime of x, when we were deriving the derivative of cosine, is 2 cos x times the derivative of cos x, which is negative sine of x. In that other problem, we pretended we didn't know what the answer was. And the derivative of sine squared x is 2 sine x times the derivative of sine of x is cosine of x. And that minus sign can be brought in front, and these two things completely cancel, giving you 0. Yeah, how could this have been done without using the chain rule as we just did? It could have been done by the Pythagorean identity. You know this is always equal to 1, it's a constant, therefore its derivative is always 0. But this is nice to confirm that way as well. Number 3 says find the first closed interval from a to b, where a and b are both positive and a is less than b, where the graph of f of x equals cosine of x squared is increasing, where its derivative first becomes positive on some interval would be what to do here. So let's find that derivative. F prime of x, I need the chain rule. Inside function is x squared, outside function is cosine of x. The derivative of the outside function, cosine, is negative sine. Plug in the inside function, multiply times the derivative of the inside function. There we go, there's the derivative. Where is this first positive? Well, first realize that when x is 0, it's 0. And when x is slightly positive, this quantity is a negative number because 2x would be positive. Sine of x squared would be positive, but we have a negative sign there. So this derivative is 0 at first, then right away it's negative. When does it first become positive? It would become positive once we get to the first positive value x, where sine of this quantity is 0, and then it'll be positive when x is slightly bigger than that. It'll be back to going to negative at the second positive value of x, where sine of this quantity is 0. Where will that happen? Okay, let's set this equal to 0 and solve for the first two positive roots. And those will be the a and the b. That'll be the answer. I'm after positive roots, so I can not think about the 2x here. Certainly this does equal 0 when x is 0 because of the 2x there. And in fact, sine of 0 is 0 as well. I can just focus on where does sine of x squared equal 0 for the first. We want the first two positive roots. For the sine function itself, its first positive root is at pi, right? Input is in radians. Sine graph goes up, then comes down at pi. Then it goes down, back up, and reaches 0 again at 2 pi. So this is going to occur when x squared is pi or 2 pi, meaning x itself is square root of pi and square root of 2 pi. Okay, and therefore that means this is the a and this is the b. And so the interval that we're after from a to b is square root of pi, comma, square root of 2 pi. That would be the answer. Let's go ahead and approximate this as well. And in fact, even use the calculator to see that it does seem right. So square root of pi is pi to the 0.5 power. That's about 1.77. And square root of 2 pi would be 2 pi to the 0.5 power, about 2.51. All right, let's go ahead and make a graph here, clear these out. So the function is cosine of x squared. That's the original function that we're thinking about here. Let's go a window from 0 to, let's go ahead and make it to 2.51. So we more easily see it here. And let's make the x scale maybe so we see a tick mark at 1.77. Hopefully that'll do what I'm hoping for there. All right, let's go ahead and graph it there. This is cosine of x squared. What were we after? We were after the first interval from a to b, where a and b are both positive, where this graph is increasing. Yeah, that's about 1.77 square root of pi. That's square root of 2 pi, about 2.51. There's our first interval where the function is increasing. Our last two problems are word problems. Number 4 says a population that varies seasonally is given for t months from January 1st by this formula that you see here. What we want to find in part A is when is the population a maximum and what is the maximum population. You actually can solve that certainly without calculus, just by knowledge of the graph of sine and cosine, sinusoidal functions. In fact, I will go ahead and graph it here first. So this is a sinusoidal function with an amplitude of 300, a vertical shift of 400, and a period that can be determined from this pi over 6th. The period, call it capital T, that's the period, is always 2 pi over the coefficient of t. We're assuming our calculator is in radian mode when we're thinking about this. 2 pi over pi over 6. The pi's cancel. This is the same as 2 divided by 1/6, which is the same as 2 times 6, is 12 months. Hey, this has got a period of 12 months. Makes intuitive sense. Little t here is in months. MOS is an abbreviation for months. And the population is P of t. We also know it's the sine function instead of the cosine function with a positive coefficient in front of sine. So its graph has to start at the midline or average value, which will be the vertical shift, 400. Well, let's put that here. And let's make this be 700. That'll be the maximum value. That's the answer to what's the maximum population. And the minimum will be 100. How did I get those? The amplitude's 300. You do 400 plus 300 to get 700, and 400 minus 100 to get 400 minus 300 to get 100. The graph's going to go up, then down, then back up again in 12 months. So this is 12. This would be 6. When is the population a maximum? It would be at 3. We will confirm this with calculus. The answer there is at 3 months. What is the maximum population? The answer there is the maximum value. The second coordinate at that point is 700. You know, what is the units? We're not given units here. It could be 700,000 people, or probably more likely animals, bunnies or something. We could even guess what the answer is for part B without calculus. When is the population increasing fastest, and what is the population at this time? It's increasing fastest when the slope of the tangent line is largest. Right here, and yeah, technically right there too. That's when the slope of the tangent line is largest. When does that happen? T equals 0 months or 12 months. And what is the population at that time? It'd be 400. Okay, so we can answer these things without calculus. But let's go ahead and use calculus to confirm it. As far as when is the population a maximum, confirming it occurs at time 3, you'd want to confirm that the derivative of this function is 0 at 3. The slope of the tangent line there is 0. Of course, it's also 0 at 9. And that's a minimum instead of a maximum. So you need some other method to know that for sure you have a maximum at 3. There is another method. There are a couple other methods called the first and second derivative test. We're actually not quite there in this sequence of videos yet. I can talk about it anyway, though. P prime of t. Differentiate this. The 300 is a constant multiple. It gets carried along. The derivative of sine is cosine. I got to use the chain rule. I plug in the inside function, and then I multiply times the derivative of that inside function, which is pi over 6. The derivative of 400 is 0. There's the derivative. Set this equal to 0 and solve for t. After the first two positive values of t were at 0, I got to think about where the cosine is 0. This extra factor of pi over 6 and the 300 there don't really matter as far as when this is 0. This is going to mean the input for the cosine function, pi over 6 times t. If I'm after the first two values where this is 0, think about the graph of cosine. The first value is where it's 0 is when it's pi over 2, the input. And the second one is where it's 3 pi over 2. Solve for t. Multiply both sides by 6 and divide both sides by pi. The pi's all cancel. 6 over 2 is 3, and 6 times 3 halves is 9. Yeah, those are the first two positive values of t where this derivative is 0 and where the original function has a tangent line with a slope of 0. And yeah, they give you a max and a min. Why is 3 a max and why is 9 a min? The first derivative test essentially says you're going to have a max when the first derivative changes sign from positive to negative near this point t equals 3 where the derivative is 0. Does this function here, this derivative, change from positive to negative? You can check graphically if you want that it does. And you're going to have a minimum where the first derivative changes sign from negative to positive. As you pass through t equals 9, you can double check that happens here as well. I'm not going to go into details. There's also something called the second derivative test. If you find the second derivative by differentiating this one, it's going to be negative at a maximum because it's concave down and positive at a minimum because the graph's concave up. Okay, you can double check that if you like. Part B, when is the population increasing fastest? When is the population at this time? You'd want to try to maximize this function by finding where its derivative is biggest. Or you can just think about the graph. It is going to be maximized at t equals 0 and t equals 12. Our last problem is a word problem that technically does involve a trigonometric function. You can see it here, the cosine function, but does not actually involve a trigonometric derivative. That's okay, it's an important kind of problem. It says that an oscillating mass m grams, gm means grams, is at the end of a spring. So you got a spring and a mass attached to the spring, it's oscillating back and forth. Is at a distance y from its equilibrium position where it would be at rest, given by this equation here, y equals a times cosine of square root of k over m times t. What in the world's going on here? If you graph this, it's a cosine wave. It goes up and down periodically. That's with an amplitude of a. That's keeping track of the fact that the mass is oscillating back and forth, back and forth, back and forth, back and forth. With amplitude a, meaning that's the distance between the extremes of the mass and the equilibrium position. The fact that it's a cosine just tells you where it starts when t equals 0, for example. And then you have this factor of t in there, square root of k over m. M is the mass. K measures the stiffness of the spring. The stiffer the spring, sort of like you might think the thicker it is, it's got a very strong restoring force. K is large, that's a very stiff spring. And if K is small, that's not so stiff, like a slinky, you might say. Not a very stiff spring, not a very strong restoring force. Part A says, what is the period t of the oscillation? How long does it take to go back and forth to go back to where it started with the same velocity? That is based on the period of this trig function. Part A, the period, like we saw in the last problem, is 2 pi over whatever the multiplier is of the little t here. That's square root of k over m. That is the answer. It's not the only way to write the answer. You could also bring the 2 pi in front and take the square root of the reciprocal of the fraction in the bottom, square root of m over k. And maybe for the purposes of taking derivatives, as we will need to do here in parts B and C, maybe it'd be best to write this as well. First, 2 pi square root of m over square root of k, and then realize that's the same as 2 pi times m to the 1/2 power times k to the negative 1/2 power. So we're not going to take derivatives of trig functions in B and C. Instead, we're going to take derivatives of this function. But wait a minute. What are the variables? You can see in part B, we're assuming k is fixed, and we're finding the derivative of t with respect to m and interpreting its meaning. And in C, we're going to do the opposite. We're going to assume m is fixed and find the derivative with respect to k. Can you do that? Can you do such a thing? And what would it mean? I mean, how can the mass change? How can the spring change? Well, the mass changes if you make it a different mass, a bigger or smaller mass. And the spring constant k changes if you make it a different spring. Now, you're not going to be able to do that like instantaneously with a physical experiment, but you can still do it. And you can think about this function here of two variables and think about making predictions about what would happen with the period of the oscillation based on what we do here. Let's do B in red here. It also, I mentioned this in a recent video that I made, might be good to use partial derivative notation as well. I could write this instead. If you're in multivariable calculus, or if you know a little bit about multivariable calculus, you'll see this kind of notation for the derivative 2. What am I doing? Why did I change these ordinary d's to sort of curvy d's? Well, it's just notation. And don't take it too seriously, other than just notation that specifies that, hey, this function t, capital T, really depends on two variables, m and k. And I can think of these variables mathematically if I want to. That's just special notation to emphasize that fact. You certainly could use this notation as I do in the problem statement itself. It doesn't really matter. We're trying to find the derivative with respect to m. Treat the k as a constant. Treating the k as a constant, you just carry it along for the ride, so to speak. We just differentiate m to the 1/2. We get 2 pi, bring down that 1/2, m to the negative 1/2. just that k to the negative 1/2 just stays as is. We can simplify this a little bit. The 2's cancel. We could write this in simplified form as pi over square root of m times square root of k, which we could also write as square root of m times k. Now, I'm not going to plug in particular numbers. I certainly could. I could plug in whatever the mass is. Maybe it's 2 grams, whatever the stiffness of the spring is, k. What would the units of k be? Newtons per unit length would be the typical thing to do. I'm not going to go into details. It's related to something called Hooke's law if you want to look into it. But maybe k has a value of 0.1 or something. And so you'd have 2 times 0.1 is 0.2. Square root of that is, I don't know, what would it be, 0.4 something. And you'd be doing pi over that, whatever you end up getting. That would be some positive rate of change of the period with respect to the mass, meaning, here's the important part, if you increase the mass slightly, make it a slightly bigger mass, same kind of setting here, you would expect the period also to increase slightly by whatever this rate of change is times the change in the mass. You could write delta m, change in the mass, or excuse me, delta t, change in the period, is approximately the rate of change of the period with respect to the mass times the change in the mass. That would be the key thing to use for your approximation. Okay? It could be used for predictions, okay, essentially. So the period is going to get a little bit bigger if you increase the mass. Does that make intuitive sense? Make it a bigger mass? It's going to take a little, it's going to go a little slower. The spring, it's the same spring because k is the same. It's, in a sense, going to have a harder time pulling it. So it's going to go a little slower in its motion. That's the prediction there. Of course, you can also figure that out just from the equation itself. You don't really need derivatives except if you're just after brief linear approximations. Part C, it says, assuming m is fixed, find the derivative with respect to k, the spring constant, and interpret its meaning. The derivative of the period with respect to k. We could also use partial derivative notation. It's not a big deal either way. Go back here, treat the m as constant. So the 2 pi and the m to the 1/2 just stay as they are. Differentiate k to the negative 1/2. The negative 1/2 comes down in front. So we get negative 1/2 k to the negative 3/2. The 2's cancel again. We can also rewrite this with square roots as pi times the square root of m divided by k to the 3/2, which can be written as k times square root of k. You also could combine those square roots. I forgot my negative sign, that's important. And get negative pi times pi over k times the square root of m over k. A number of different ways to write it. Okay, but it is negative, and you can plug in particular values of m and k to evaluate the derivative in a certain situation. It is a rate of change of period with respect to changes in the stiffness of the spring. In other words, with respect to changes in the spring itself. And if you increase k a little bit, if you make it a little bit stiffer spring, stronger spring, and plug this in there, you would get a negative change in the period, meaning the period's going to go down a little bit, meaning the motion's a little faster. If you make it a stiffer spring, it's a little faster motion because it's a stronger spring, a stronger restoring force. Hope that makes sense. Thanks for watching.